Welcome back to The Explainer. Grab a marker because today we are heading straight to the virtual whiteboard to unpack one of the absolute most fascinating and honestly most challenging areas of back-end engineering. We're talking about distributed coordination systems. So I want you to imagine a scenario for a second. You've got a massive cluster of hundreds of independent computers. How do they actually agree on a single indisputable truth? Now, it sounds pretty simple on the surface, right? But remember, in a distributed system, there is no perfectly synced global clock, and there's definitely no shared memory. They only have a network to communicate through. And as we all know, networks can be incredibly, frustratingly unreliable. Here is our roadmap for today's session. We're going to cover the core distributed coordination problem, look at the coordination service solution, dive into leader election, unpack locks and leases, explore membership and discovery, and then tie it all back to real-world architectures. Let's kick things off with the problem itself, the absolute chaos on the network. Basically, distributed coordination is the process of getting independent, completely unreliable nodes to agree on a shared system state. And the catch? They are connected by an asynchronous network. Because network messages get delayed or just dropped completely, and because server nodes can crash at literally any second, coming to a safe, shared decision is an incredibly difficult engineering hurdle. If those nodes fail to agree, you run straight into what backend engineers dread the most, the split brain scenario. It's exactly what it sounds like. Think of a system literally losing its mind. It splits into two conflicting halves, where two separate nodes simultaneously believe that they are the one true leader of the database. So what actually happens when two nodes both think they're in charge? Utter catastrophe. Both nodes start accepting client rights at the exact same time. And because there is no clear unified process for resolving those conflicting rights, you're facing a massive likelihood of permanent data loss. Or even worse, silent data corruption creeping across your backend databases. Without coordination, the entire system's integrity just completely falls apart. So how do we fix it? That brings us to our second point, bringing order to the chaos with a coordination service. To prevent this nightmare, we introduce a highly specialized component. It has a really small, highly reliable footprint. It uses incredibly advanced mathematical consensus algorithms to remain fault-tolerant, and it keeps its critical data entirely in memory for lightning-fast speed. We're talking about heavy hitters like Apache Zookeeper or etcd. These are not your general-purpose databases for storing user profiles. They are tiny, robust fortresses designed solely to store system-critical decisions safely. And this introduces a super powerful concept, outsourcing consensus. Building consensus protocols from scratch? Notoriously difficult and deeply prone to bugs. So, rather than forcing your main application to constantly reinvent the wheel, you outsource the heavy lifting. You let the coordination service handle the tricky parts, like failure detection and getting nodes to actually agree. Moving on to point 3, electing a single leader, because there can literally be only one. Think of a leader election like a race, where the winner gets the crown. Step 1, all the nodes race to acquire a distributed lock inside that coordination service. Step 2, the very first node to succeed grabs the lock and becomes the single leader. Step 3, everyone else sees the lock is taken, concedes, and becomes a follower. And step 4, if that leader crashes, or say its network cable gets unplugged, the service releases the lock, and a brand new election is instantly triggered. It's beautiful. But, of course, distributed systems are never quite that simple, are they? Enter the zombie node. This happens when a leader node doesn't actually crash, but instead suffers a massive stop-the-world garbage collection pause. The server literally freezes, the whole system assumes it's dead, and a new leader gets elected. But then, minutes later, the zombie node wakes up. It has no idea it was asleep, and it wrongly believes it is still the leader. Which leads us to point 4. How do we protect our shared state from these zombies using distributed locks and leases? Imagine Client 1 gets a lease on a lock, but then Client 1 experiences that brutal garbage collection pause. Its lease quietly expires in the background. So Client 2 steps in, gets a fresh lease, and starts writing data. But then our zombie, Client 1, wakes back up. Because it hasn't checked a reliable clock, it thinks its original lease is perfectly fine, and it fires off a write request to the storage. Boom, 2 clients writing at once. You get a massive crash and corrupted files. And this right here is exactly why standard locks fail in distributed environments. A standard lock relies entirely on the client knowing its time is up. The definitive engineering fix is something called a fencing token. With a fencing token, the coordination service doesn't just say, hey, you have the lock. It hands out an incrementing ID, like a ZXID transaction ID in Zookeeper. The storage layer then actively checks this token before accepting any data whatsoever. In this setup, the storage server acts like a bouncer at a club. Client 2 shows up with token 34, it's allowed to write. But when our zombie client 1 finally wakes up and tries to write with its old, dusty token 33, the storage layer looks at the number, sees that it's outdated, and explicitly rejects the write. The zombie gets bounced, and our data remains safe. Let's look at point 5, membership and service discovery, or simply, who is actually alive right now. In a large database, your data is partitioned across tons of different nodes. In cluster layouts, they change constantly. Zookeeper maintains the authoritative mapping of exactly which partition lives on which active IP address. The routing tier just subscribes to Zookeeper, mapping client requests perfectly to the right destination, even as the whole cluster shifts and heals behind the scenes. But how does it know who's alive? Through heartbeats. Application clients maintain long-lived network sessions, sending periodic heartbeats to prove they're still functioning. Zookeeper represents this internally using what's called an ephemeral node. If a server crashes and those heartbeats stop, the session times out, and the ephemeral node automatically vanishes. This elegantly triggers automatic failover and routing updates without a human ever having to touch a keyboard. Okay, point 6. Let's bring it all together with some real-world examples. You are likely interacting with coordination systems every single time you use a modern app. We're talking distributed job schedulers, assigning massive workloads without duplicating tasks, Kafka message brokers tracking which node owns which message partition, distributed databases like HBase routing reads and writes across a cluster. Ultimately, it's about giving massive systems the superpower to recover automatically from hardware failures, completely seamlessly. The ultimate takeaway here is all about centralizing the truth. Coordination systems are incredibly powerful precisely because they act as a localized bottleneck of truth for your entire cluster. But because they hold that ultimate authority, they demand absolute strictness in their correctness. Messing them up, like say forgetting your fencing tokens, compromises your entire architecture. I want to leave you with this thought. Coordination systems are the brainstem of your infrastructure. Treat their correctness as absolutely critical because if they fail, the whole system loses its mind. I really hope this leaves you with a profound respect for distributed coordination infrastructure. It's complex, it's challenging, but man, is it fascinating. Keep learning, and I'll see you on the next explainer.